Hi everyone, we are Group 11 and we are going to present you our project on popularity bias in session-based recommendation. So what is popularity bias? In a recommender system dataset, users are more likely to provide feedback on more popular items because they get exposed to those items more often. This means the observed user feedback collected by a deployed system, generally a simpler model like KNN, will be biased towards those popular items. This closed loop feedback can lead to bias evaluation results that favor simpler models. Our framework to test this phenomenon is the Simpson's paradox. The paradox happens when model A outperforms model B on the dataset, but when we stratify the dataset into multiple subsets, model B actually outperforms model A on at least one of the strata. The Simpson paradox has been studied by researchers on traditional content-based recommender systems. In this project, we want to extend the study to session-based recommender models as well. This is an interesting problem because it has been observed that in the session-based setting, simpler models like KNN can outperform deep learning-based models in many domains. We want to know if this is really true through the lens of Simpson's paradox framework. We use 3 data sets. Two of them are retail data sets, and the other one is a music playing data set. You can see that the music data set actually has a much longer session length than the retail ones. We also removed extremely short sessions and very rare items. Here is a snapshot of the data set itself. It's basically a log of item interactions with timestamps.
So to compare the 2 types of model, we selected skNN from KNN-based models. For deep learning models, most approaches utilize sequence models such as RNNs. We chose GRU for RAC as it is a widely used model that encodes a session with GRU. The propensity score of an item I is estimated using the item's number of raw observations in the dataset. We use 2 common metrics. Hit rate measures whether the target item appears in the recommendation list. MRR also counts for the rank in the recommendation. So the primary results is that for Diginetica, KNN outperforms GRU for RAC. For Retail Rocket, KNN outperforms GRU for RAC and MRR, suggesting that it does a better job on pushing the target item towards a higher rank in the recommendations. For Sturdy Music, GRU for RAC outperforms KNN. We'll not be focusing on that during this presentation. So the question is whether stratifying actions to Q1, where target item has low popularity, in Q2, and then apply 2 models to different strata improve the performance. So ideally, for each test session and for each prediction, we use the target item's propensity score to stratify the action. However, in real life, the target is unknown. So we'll instead use the average of the previous item propensity scores. Here in the results, we plot the results if we apply different models to different strata and experiment with different propensity score thresholds. This is for Diginetica datasets stratified by target items propensity, where x-axis is the stratification threshold and data below x percentile belongs to Q1. We observe that GRU for RAC performs better on Q1 data and KNN is better on Q2 data. We then approximate this graph by using the average of historical item propensity instead. We observe the same trend here, and we use this graph to identify the stratification threshold such that GRU for RAC outperforms KNN on Q1, which are really visited items, the long tail of the propensity score distribution, and KNN takes lead on Q2. So the cutoff here is the 10th percentile. After applying GRU for RAC only on Q1 data and KNN only on Q2 data, we see that the results improve when comparing to the primary performance of GRU for RAC. However, this improvement is not significant and not stable when comparing to the primary performance of KNN. We got a similar observation for the Retail Rocket dataset.
So to actually make use of this finding, we did model ensemble. We assigned weights to the scores output by KNN and GRU for RAC. If the input is in a lower propensity zone, we assign higher weights to GRU for RAC and higher weights to KNN otherwise. So this is what it looks like when we put it in a formal term. The result looks pretty promising for the retail datasets. We assign 0.8 to the better model, we get the best results. The performance of weight being 0.8 also outperforms that of weight being 0.5. This means our improvement didn't just come from the example alone, but from the weighting by propensity score. So in conclusion, stratification based on popularity does have an impact on model performance for the retail domain, but this effect needs to be further studied for other domains as well. aside from this finding, we want to highlight our contribution and novelty on this new way of handling popularity bias in recommendation systems. Instead of reducing it, we chose to incorporate it into our model development process.